Solving equations with logs and exponentials involved. So we did some of these at the beginning of this chapter. Things like 4 to the 2x minus 1 is equal to 8 to the x minus 5. And this is considered an exponential equation. We got the bases exactly the same. So this would be 2 squared raised to the 2x minus 1 is equal to 2 cubed to the x minus 5. And I'm going to do this really quickly. The exponents then, since the bases are the same, have to be equal, and we're going to distribute. So this would be 4x minus 2 is equal to 3x minus 15. Okay, and then when we solve for x, we're going to get x is equal to negative 13. So that's the way we can solve if there's a one-to-one relationship that we can get the bases exactly the same. The same thing happens with log. Like if you had log base 2 of 3x minus 1 is equal to log base 2 of 5x plus 1, then since it's a one-to-one relationship, because the bases are exactly the same, and the only thing on both sides is log, there's no weird stuff added on besides that, we can just drop the logs and talk about the domain. So the domain is 3x minus 1, have to equal the domain of the other side, 5x plus 1, and we can solve. So those are relatively simplistic types of examples. So the one. All right, so this is just another example of the one-to-one property type of equation with an exponential. So the first thing you need to do is, of course, get the bases exactly the same. So we're dealing with 36 and 6. Even though there's a square root there, we can kind of deal with that in a second. So the base we need here is definitely 6. So if I'm going to change 36 into a base 6 number, it's going to be 6 squared. So we're going to get 6 squared is the same as 36 raised to the 4 minus x is equal to, now the square root of 6 might be a little tricky, but you just have to remember that square roots have a power associated with it, in this case 1/2. So when I write this, it's going to be 6 raised to the 1/2 power, and then that's going to be raised to the x plus 1. So basically you're just technically rewriting the first line as the second line. Now we have a situation where it's power to a power, so we're going to multiply 2 times the quantity 4 minus x, and over here the same thing, power to a power, we're going to multiply 1/2 times x plus 1. So that'll get us to 6 raised to the 8 minus 2x is equal to 1/2 x plus 1/2. Oops, I forgot my 6. 6 raised to the 1/2 x plus 1/2. Now that the bases are exactly the same, the one-to-one property kicks in. If the bases are the same, the exponents have to be the same. So that generates this equation. It's not that we're canceling the 6's. We were just recognizing the powers have to be equal. Now personally, I'm not a fan of fractions, so I would go through this and multiply everything by the common denominator, which is 2. And that way you don't have to work with fractions at all. So this is 16 minus 4x is equal to x plus 1. All right, and then just solve the equation. Get the x's on one side and the numbers on the other. So I'm going to add 4x. And then subtract 1. Oh, this came out nicely. And then finally, divide both sides by 3. I'm always in the habit of showing the division because I've always made silly mistakes in this place. And look at that, I already made it because I was thinking of the answer. So I'm going to divide both sides by 5, and we're going to get x equals 3. Now, because these are exponential functions up there at the very top, then this is definitely an answer to it because the domain for exponential functions is all real numbers, so there's no way that it can't be 3. And you can go back and test it out if you want. If you come back up here, plug it in, you're going to get 4 minus 3, which is 1, so you'd get 36 to the first. On the other side, you would have 4, and then The square root of 6 raised to the 4th is the same thing as 6 squared, which is 36, which is the other side. All right. Now, one-to-one property also works on things like logarithms. So if I have something like log base 2 of x minus 1 plus, let's get a little crazy here, log base 2 of x plus 1, and it's equal to log base 2 of 15. All right, so sometimes we might have to use other properties, like here we have a property of logarithms. There's logs on both sides, but there's too many on the left-hand side. So what we can do is, if you have two logarithms and they're added together, that means the insides can be, condensed. So we can write this as a single log. So when we write it as a single log, we're going to have the first one, which is x minus 1. The addition tells us the original stuff was multiplied, so we'll get x plus 1 over here, and it's equal to log base 2 of 15. Now it's important that the bases of the logarithms are exactly the same in this case. So because logarithms are a one-to-one function, and they're equal to each other, then the insides must also be equal. So we can just take that assumption that the insides are also equal and write this equation. And then solve. So expand the x minus 1 times x plus 1. And there's two ways about this. We can subtract the 15 and factor. That's what most people would do. Well, actually, no. Most people would not do that. Most people would add the 1. And then square root both sides. The danger of doing it this way is a lot of people forget to put this down as the next step. When you square root both sides of an equation, you have to plug in a plus or minus. So here we would get x is equal to plus or minus 4. So sometimes it's better to actually get it equal to 0, subtract the 15 from both sides, and then factor the x squared minus 16, and that way you don't lose one of the answers. Now sadly, one of these answers doesn't work because the domain of logarithm is when you graph, the log graph. The graph hugs the y-axis, hits this point 1, 0, and then goes off in this direction. So the domain of this thing is 0 to infinity. So we can't have any answers on the inside of a logarithm that are 0 or negative. Well, when I plug this guy in to the very top, if I plug it in here, I'm going to get negative 5. If I plug it in here, I'm going to get log of negative 3. So that answer cannot exist. So we can kind of just say it's not part of the domain, so it can't be part of the solution. So the only number that works is this positive 4. Now be careful. It's not that the answer is positive or negative. It's when you plug it in, it generates a negative number on the inside of a logarithm. So make sure you test it out before you start just canceling the negative answer. So this one only has one answer, x equals 4. Another useful tool for solving exponential equations is using the power property of logarithms. In other words, log base b of a raised to the power, where you bring the power and drop it out front. You can use this property to solve those previous equations up here, though it does get kind of tricky with variables on both sides of the equation. So with this type of equation, where the variables are only on one side and there's just a single constant on the other side, the logarithm property comes in kind of handy. So what we're going to do here is we're going to log both sides. Now I'm going to choose a base that makes more sense. For instance, this is 10 raised to the 3x minus 2, so I'm going to use the common logarithm. Generally, you don't want to do things like log base 2 because your calculator doesn't work real well with log base 2 unless you use a change of base formula, which we'll get to. All right, so what we're going to do is we're going to common log this because a common log has a base of 10 and the left-hand side has a base of 10. So when possible, using a common log if you have a log base 10 exponential, then it'll work out really nicely. Now, if it was 5, I would probably still use a common log or a natural log to solve it. It just gets a little bit messier. So this one should work out rather nicely. So we're going to common log both sides, and then just write the sides inside of these parentheses. And this is totally legal because whatever I do to the left-hand side of the equation, I just do the same thing to the right-hand side of the equation. And this definitely works because it's a one-to-one function that I'm applying to both sides of this equation. All right, so what happens here now is this power sitting up top is going to drop down in front, or we could look at it this way. The log base 10 of 10 raised to those two are inverse functions of each other, and they're going to go poof. But I'm going to drop it out front just to remind you of another property. So if I drop it out front, I definitely want to put it in parentheses because it's a two-term polynomial, and whatever comes after it is going to multiply this entire two-term polynomial. So next to it is going to be times common log of 10. All right, and this is going to equal, there's not much I can do with this one, log of 20. All right, now the log of 10, what power do you raise 10 to get to 10 is just 1, and that becomes 1 times 3x minus 2. So we're going to get 3x minus 2 is equal to log of 20. And now we can start solving for x. Log of 20 is just a number. You can type it in your calculator, get some ugly decimal for it. But I want to leave it exact, so I'm going to add 2 to both sides. And I'm going to write it this way. You can write log 20 plus 2, but I like putting the numbers in front of logarithms. And then divide both sides by 3. And this would be considered the exact answer. Now, if we go typing this into a calculator, and we'll get some ugly decimal 1.1-ish. So then we can talk about an approximation of about 1.1. There are reasons for one or both of these answers. The first one is an exact answer, so then you can get as many decimal places as you want out of it. The other one's good for like word problems, applications. So we have a physical answer like 1.1 feet or 1.1 hours, something like that. All right, another place to use the logarithmic power of bringing a power down is in this situation. There is a problem with it though. Over here, the 10 and the logarithm were touching each other. So when they hit each other, they kind of go poof because they're inverse functions. The problem here is if I put an ln here, which by the way is the inverse function of e, it's hitting the 17 and not the e itself. So the first thing you have to do in an equation where the exponential function is kind of buried is to get it by itself. So I'm going to treat this whole piece as a single variable and get it by itself. So if there was, plus 17 over here, I'd get rid of that plus 17 first, and then the other 17. Okay, so the first thing I'm going to do is get the 17 away from the e to the whatever. And then the only way to get rid of it is division because the operation connecting it to the e is multiplication. And I'm not going to rewrite 150 divided by 17 as a decimal. I'm just going to leave it alone for now. I mean, exact answers are much better. And this is equal to e to the 3x minus 2. Now that the e is kind of by itself, bared, gotten away its layers, we can ln both sides because ln has the base e as a logarithm. It makes it the easiest one. You could use a common log here. It would still work. It would just be a little bit more messy. So I'm going to ln both sides. And again, that's totally legal because it's a one-to-one function. I'll leave this as 115 over 17. 150 over 17. And then over here, the e to the 3x minus 2. All right. Now, eventually, you're going to kind of skip this step and go to the next one, which is fine. As long as you don't do anything illegal, you should be safe. So I'm going to bring the power down. Now remember, it's a two-term polynomial, so I'm going to bring it down inside of parentheses. And it's going to be times ln of e, but ln of e is equal to 1. So you either cancel them as inverse functions and bring down the 3x minus 2, or you can bring the power down out front and then realize that ln of e is just equal to 1. Either way works perfectly fine. And then I'm going to go through and solve for x. So if ln of e is equal to 1, I basically don't have any of this around, because 1 times anything is itself. And then I can start solving for x. So add 2. So this becomes 2 plus ln of 150 over 17 is equal to 3x. And then divide both sides by 3. So this is the exact answer, not the decimal answer. So if you want to find out what the decimal answer is, or the approximate answer, you'd have to type it into a calculator. About 1.39. So x is approximately 1.39. All right. So that's how you can use the logarithmic power of bringing the power down. It is a very useful way of solving an equation, and it comes in very handy for applications of logarithms and exponentials. Ones I want to conquer in this section are the ones that don't have a common base. So things like 5 raised to the 3x minus 1 is equal to some prime number 17. So in this case, we can't create a common base. So the only option is to log both sides. So if we log both sides, and I might have done this several times for more simple things, we would get this equation. And the power of logarithms is it brings the powers down. So it would be in a position where we can solve them. Just don't forget that 3x minus 1 has to be put in parentheses because it's a single power, and it's going to be times log of 5, and it'll equal log of 17. And then we're going to start solving for x. Now, one of the easier ways to do it is to, well, some people would distribute the log of 5, which is perfectly fine. I wouldn't suggest it because it'll just get kind of messy. So the easier way to deal with, log on both sides and multiplication here is divide both sides by log of 5. It's going to be an ugly decimal anyway, so log of 17 divided by log of 5 is just going to be another ugly decimal. And it'll be a little bit more an accurate ugly decimal rather than having a decimal in this position distributed, a decimal in this position, and then a lot of rounded decimals being thrown around. So it's easier to put them on one side so that the rounding error becomes minimized. So that would leave us 3x minus 1 is equal to log of 17 over log of 5. And then we're going to add 1 and divide by 3. So in the end, we're going to have, 3x is equal to this ugly number. And I'm keeping it here so I don't have any rounding error whatsoever. These are exact notation so far. And then divide by 3. And this, or probably better yet, multiply by 1/3. So this would be 1/3 of log of 17 divided by log of 5. Oops. Minus 1. And typing this into a calculator, we get x is approximately going to equal 0.25 if we round to the nearest hundredth. 3458 is the rest of it, and I highly suggest you type this into your calculator to make sure you get my approximation so you have a good feel for how to enter much more complex expressions into a calculator. All right, so let's change gears a little bit and make it uglier. So for instance, if we have something like 3 to the 2x plus 1 is equal to 5 raised to the 4x, then it becomes a little bit more complex than the last one. So I just wanted to show you a trick. we're going to do the same thing. We're going to, ln both sides. Well, in this case, I'm going to ln instead of log. So it doesn't matter which one you use. I just prefer ln because it's less writing. All right. So this becomes ln of 3 raised to the 2x plus 1. This becomes 5 to the ln of 5 to the 4x. So again, the point of ln'ing both sides or logging both sides is so the power gets dumped down out front because the x's cannot be solved for while they're up high. So this side is going to become 2x plus 1. Don't forget the parentheses because it is a single power times ln of 3 is equal to 4x times ln of 5. And whether you put parentheses around the 4x in this situation, it's not going to matter because it's a single term. All right, now if we started solving for x, again, we might start thinking, let's distribute. And again, it's going to get kind of messy. So we're going to do the same step that we did earlier, put the ln's on the same side. So I'm going to divide both sides by, why not, ln of 3. You could choose to divide both sides by ln of 5. It really doesn't affect anything. But I like the 2 ln's put together on one side of the equation. So that leaves us with 2x plus 1 on this side. The ln of 3 has been moved, is equal to 4x times this ugly number, ln of 5 divided by ln of 3. All right, to keep solving for x, we're going to need to move the x's onto the same side. So I'm going to choose to subtract 2x from both sides. So if I subtract 2x, I'm going to get 1 equals 4x times this ugly number, and then minus 2x over here. Okay, so at this point, a lot of people are going to change that ln of 5, ln of 3 into decimals. If you do, keep about 3 to 4 decimal places to make sure you don't run into a lot of rounding error. I'm going to keep all the terminology exact for a little bit. So what these two terms, and the two terms are this big ugly term and this term, what do they have in common? Well, they have an x in common, so I can factor it out. So if I kick the x out, what's left behind is 4 ln of 5 divided by ln of 3 minus 2. And then finally, to solve for x, I'm just going to have to divide by this ugly mess. So I'm going to get x is equal to 1 over 4 ln of 5 divided by ln of 3 minus 2. And it's really important to have these parentheses here for the calculator purposes. So I'm going to type this in and see what we get. So this answer is approximately 0.26 if we round to the nearest hundredth. It's 0.25907 if you want some more decimals. And again, I highly suggest you type this into your calculator and see that you can get this answer. It's good practice. All right, so here's an equation that has logs in it, but it's not a log on one side and a log on the other side. There's other stuff going on. Most importantly, this 3 here. It can't be included as a single log, and then we have this plus sign. It kind of gets in the way. All right, so in this case, what we need to do is combine the logs. I mean, we have a plus sign in between them, so the clue should be we're going to put them together. So if we put them together, we're going to get a multiplication between the two terms. So it becomes 1 log of base 2 of x times x minus 7 is equal to 3. So we get a single log now on one side, and it's equal to 3. So the next step should also be kind of obvious. The base of this exponential, or this logarithm, is 2. The exponent is 3. And the number is this ugly mess here. So this, if we convert it into an exponential notation, becomes 2 to the third is equal to, and I'm going to expand it, x squared minus 7x. And we get a quadratic equation. So 2 to the third is equal to 8. And because it's got an x squared term and we're never going to get rid of it, we're going to get it equal to 0. So subtract the 8 across, and we get this polynomial that looks like it could be factored. So let's factor it. So factors of 8 that subtract up to -7, which would be, let's see, 8 and 1. So we're going to get x8, x1, and the bigger number has to be negative, so it's going to be x minus 8 and x plus 1 because we need a -8 at the end. So our two solutions are going to be x equals 8 after you set your factors equal to 0, and x equals -1. Great. So if you leave both of these answers, well, it's going to be marked partially wrong. And the reason for that is the domain of logarithm, if you remember the graph, and this is why graphing sometimes comes in to become important, is that logarithms, let's go orange, crawl up the negative y-axis, hit this point 1, 0, and then slowly grow. So the domain of this function is not including 0 all the way to infinity. So if that's the domain of this, and we take x equals -1 and plug it in right here, we have a problem. You're trying to take the log of a negative number, and negative numbers are not part of the domain. So this cannot be a solution to this equation. It's always best to check both answers when the domain starts to get tricky. Exponentials don't have that problem because exponential graphs have a domain that is all real numbers. So x equals 8 seems to work out, well, it definitely works out in x, and 8 minus 7 is just 1, so it works out fairly well. So this is the only solution to this equation. So one more type of equation that you might run into is one that is considered quadratic form. Now, if you don't remember quadratic form for Math 171, this will be a nice little review. So I know this is in quadratic form because it is 3 terms, it's equal to 0, and the powers, like e to the x here is to the first power, and e to the 2x here is to the second power. So this is what's considered quadratic form, that it has the right setup. And to make sure it actually does, we're going to do the U substitution thing. Now, if you didn't use a U substitution technique, this is actually a very good technique to get used to. So we're going to let U equal, and it's always the middle variable term. So in this case, just e to the x. So we don't want anything else, just e to the x. So U is equal to e to the x. And then we're going to square both sides of that equation. That should give us the first term. So when we do that, we have this power to a power situation where you would multiply. So this becomes e to the 2x. So where u is equal to e to the x, we're going to put a u in this position, and u squared is equal to e to the 2x, which is this position. So when we write our new equation, it's going to be 2u squared plus 5u minus 3 is equal to 0. And what that does is it allows you to see it as a regular quadratic function setup. Now, if you want, you can solve this using quadratic formula, but I highly suggest you try factoring it first. So factoring it, we would multiply the first number times the last number. So this would be 2 times 3 is 6. And we're looking for factors of 6. If you've never done this type of factoring before, it's one of the easier ways of doing it. We're going to put the 6 here. It's going to be negative. This negative means the two numbers are going to be opposite signs. So we need two numbers that subtract up to 5 in this case. So I know that those factors are going to be 6 and 1. It's going to be a positive 5, so the 6 gets a positive and the 1 gets a negative. Now this technique is called the X method is most common. But one problem with the X method is people think it's just 6 and -1 are the answers. Well, they're kind of the answers that give you the positive 5, but because the lead coefficient here is not 1, we have to kind of do a little bit more side work. So we're going to take the 6 and we're going to divide it by the lead coefficient. We're going to take the -1 and divide by the lead coefficient. So here, if it reduces, it's nice, like this one is 3. But if it doesn't reduce, we're going to move the 2 kind of to the front of the problem. So this one becomes x plus 3. Well, in this case, it's u. So u plus 3. And the other one, we're going to move the 2 up front. So we're going to get 2u and then the -1 from the top. So when we factor 2u squared plus 5u minus 3, we're going to get u plus 3 and 2u minus 1. Now, if you did the quadratic formula, you would get answers of 1/2 and -3, and then you can go from there if you wish. All right, so I'm going to solve both of them, and I'm going to get u is equal to -3, and u is equal to 1/2. Add 1, divide by 2. But u is not what we're trying to solve for here. We were originally trying to solve for the x in the term e to the x. So you always have to go back to the first substitution you did, which is this one. Not the u squared one, the u equals e to the x. So this u is the same thing as e to the x, and it happens to equal -3. And this u is also e to the x, and it's equal to 1/2. Well, there's a problem with e to the x equals -3. Graphically, if we're going to graph e to the x, it's an exponential function. And the graph hugs the negative x-axis, hits this point 0, 1, and then grows infinitely large. Nowhere under this graph is the value of e to the x equal to a negative number. They're all positive. They're all above the x-axis. So there's no answers down here. So there's no way that e to the x can equal -3. So that's just a not part of the range in this case. So this was not going to give us an answer. If I went through the process and tried solving it, it would also show me that it really can't be part of the answer. All right, so e to the x equals 1/2. I still have to solve for x, so I'm going to ln both sides. Bring that x down, and also the ln and the e are basically going to go poof. I hate saying the word cancel. That's usually for solving equations. So the ln and e are touching each other, so they're going to go away. And we're going to be left with x on this side equals ln of 1/2 or ln of 0.5. Either one works perfectly fine. And that is a perfectly fine solution to this quadratic form type of equation.